Welcome to Lecture 6, in which we will discuss the BB84 Quantum Key Distribution Protocol. The idea here is that Alice and Bob want to establish a private key or sequence of zeros and ones. And I want to stress that they want this to be private. They don't want anybody else to know the sequence that they have. So here's Alice, and here's Bob, and here is Eve, who potentially wants to intercept this key that Alice and Bob are trying to communicate or trying to establish. Now you see here again, this picture is from page 19 of your textbook. This thick arrow here, this bidirectional arrow that also comes down here, represents a classical channel which is public. Anybody can receive the messages that are sent along that channel. Then there's also a unidirectional quantum channel going from Alice to Bob, and along that channel Alice will be sending information about her sequence. It will be encoded in photons, and so these photons will be sent along this quantum channel. And there is the potential, now this quantum channel is hoped to be private, that's the intention, but there is the potential that Eve could intercept information on this private channel, but we'll see how the nature of this protocol would make that sort of a futile effort. So let's get down now to more details. Again, now Alice and Bob are trying to establish this private sequence of zeros and ones that will be known only to them. So Alice starts with this initial random sequence, which we will call X, and I've just randomly chosen 0 or 1. And of course, in a real application, this would be much longer, but I'm just showing you this as an example, a short example. I think if we can understand this, we would understand the longer case as well. Now, in addition to this initial sequence, X sequence, Alice has something that I'm referring to as the basis sequence, and that will be labeled A, and it's also a random sequence of ones and zeros. And finally, Bob also has a basis sequence, and of course these sequences, since all three of these sequences are random, they could be generated just by tossing a coin. Alice could toss a coin. Let's see, this is 1, 2, 3, 4, 5, 6, 7. So she could toss a coin 7 times to establish the X sequence, 7 times to establish the A sequence. Bob could toss a coin 7 times to establish this B sequence. Now, initially, Bob knows nothing about either one of Alice's sequences. Alice knows nothing about Bob's sequence. And then with this protocol that I'm going to describe, Bob is going to create a Y sequence, and the way in which that will be done will be described now. Now, the first thing we need to know is the following. When A equals 0, Alice will use the standard basis to encode her bit as follows. If she wants to encode a 0 with the standard basis, then she will encode it with the up arrow, and if she wants to encode a 1 with the standard basis, she will encode it with the horizontal arrow. On the other hand, when A is equal to 1, Alice will use the Hadamard basis. To encode her bit as follows. And here, if she wants to encode a 0, she will use this cat, which is the same as 1 over square root of 2 times the vertical cat plus the horizontal cat. And if she wants to include, if she wants to encode 1, then she will use the second Hadamard cat, which is the same thing as 1 over square root of 2 times the vertical cat minus the horizontal cat. So, let's just make sure we understand that. So, for this first bit, 0, since A is equal to 1, Alice will use the Hadamard basis, and so the first photon that she sends, since it's a 0, will be this. The next photon she will send, okay, since A is equal to 0, she's going to use the standard basis. And since she wants to send a 1, it will be the horizontal cat. Then the next next value of A is still 0, so she still uses the standard basis. This time she wants to send a 0, so she'll send the vertical cat. And so on. Now, she's sending this information to Bob, and Bob must have a sequence for measurements. So what will happen there is much the same. When when B equals 0, Bob will measure using the standard basis, and when B equals 1, Bob will measure using the Hadamard basis. So let's try to predict now what Bob's Y sequence would be. Okay, so for the first bit, A is equal to 1, so Alice is going to encode using the Hadamard basis, and since she wants to send the bit 0, she will send this cat. 1 over square root of 2 times the vertical cat plus the horizontal cat. Now, since Bob has a B for his measurement sequence, we come down here and we recall that means that he will be measuring in the standard basis. So the basis that Bob is using to measure the signal does not match the basis that Alice used to generate the signal. This is the cat right here. Remember, this is the cat that will be traveling down the quantum channel toward Bob, but he's using the standard basis to receive it. And so therefore, since he's using the standard basis, what he will measure is either the vertical cat or the horizontal cat. Even though this 45-degree cat is the one that's coming in. He will not measure that because he's not using the Hadamard basis. He's using the standard basis. So he's either going to get the vertical cat or the horizontal cat. And as we can see right here, the 45-degree cat is equal to 1/2 of the vertical cat, 1 over square root of 2 times the vertical cat plus 1 over square root of 2 times the horizontal cat. So half the time Bob will measure the vertical cat and half the time the horizontal cat. And that's all we can say. So I'll just put a question mark there and say 50%. I'll mark it like this: 50% vertical, 50% horizontal. That's all we can say about the first bit that Bob will measure. Now let's go to the second bit. Well, in this case, since A is equal to 0, Alice will use the standard basis to encode this bit now, which is a 1. So she'll send a horizontal cat to Bob. And likewise, since B is also equal to 0, Bob will use the standard basis to measure. And so he'll be using the same basis to measure. This is the photon that Alice will send, and so that is exactly what Bob will measure. So Bob will measure the horizontal cat for sure. There's no ambiguity in this case. Now, in the next case, when Alice wants to send her third bit, well, A is equal to 0, so she'll use the standard basis. And since she wants to send a 0, she will send, or encode a 0, she will send the vertical cat. But Bob has B equal to 1 for the third bit here. And so, therefore, since B is equal to 1, Bob will use the Hadamard basis. And when he uses the Hadamard basis to measure the vertical cat sent by Alice, he will get 1/2 the time. He will get the 45-degree cat. So we'll put, it's uncertain what he will get, but 50% of the time it will be this, and 50% 135 degrees. And I believe you can see how this is going to go. Note that any time that A is equal to B, it means that Alice and Bob will be using the same basis, and therefore Bob will get exactly the signal that Alice sent. So for instance, here in this first case, when A is equal to B, Bob knows, well, since it was a 1 and A was equal to 0, Alice sent a horizontal cat, and that is exactly what Bob received. Likewise here, this is exactly the same situation. A and B are both 0, and Alice wants to encode a 1. So again, in this case, we can be sure that Bob will receive the horizontal cat. In this case, A and B are both 1. So here again, Alice and Bob are using the same measurement or the same measurement basis, and therefore Bob will receive exactly the signal that Alice sends. Now let's see what that signal will be in this case. Since A is equal to 1, Alice will be using Hadamard basis, and since the bit she wants to encode is 1, she'll send the 135 degree cat, and so that's exactly what Bob will receive. But in any of the, and that's all the cases in which A and B are the same. But now, in any of the cases, as we've already seen 2 examples here, in any of the cases where A and B are different, there will be uncertainty as to what Bob will receive. Let's just go ahead and fill in these last 2 cases. Here in this one, since Bob is using the, since B is equal to 0, Bob will be using the standard basis, and Alice, since A was equal to 1, Alice will use the Hadamard basis, and since she wants to encode a 0, she'll have the 45 degree cat. But since Bob is using the standard basis, he'll get either the vertical cat or the horizontal cat, and he'll get those 2 50% of the time. So 50% up, 50% horizontal, and then likewise for the last one. In fact, that's exactly the same situation as the one we just did here. I'm saying that this and this are the same, so we again get 50% up and 50% horizontal. So it's easy to see after going through a few examples like this, and if you did not get the results that are shown there, be sure to stop the video and review this, ask a question if necessary. But I hope that you see that the only time the only time we know for sure what Bob will receive is when A and B are the same. So now, how does this procedure work? Well, Alice has her sequence, her X sequence, and her A sequence. And remember, those are known only to Alice, not to Bob. Bob has his B sequence, and that's known only to him, not to Alice. So they go through the procedure that we have just outlined. And once again, I want to make sure you understand the first bit that Bob will receive is uncertain. There's a 50-50 chance that he'll get a 50% chance that he'll get the vertical cat, 50% chance he'll get the horizontal cat. The second signal will definitely be a horizontal cat. The third one will be 50% 45 degree cat, 50% 135 degree cat. The fourth one will be 50% chance of a vertical cat, 50% chance of a horizontal cat. The fifth one will definitely be horizontal cat. The sixth one will definitely be 135 degree cat. And the last one will have a 50% chance of being an up cat, 50% chance of being a horizontal cat. So now, how do Bob and Alice establish their key? Well, what they do is after the bits have been sent, and they can do this after each one, or they can do this after the entire string. But after the entire string, let's just say after the entire string has been sent, Bob and Alice will then talk on the classical channel. Now remember, this means that Eve can hear this. Bob and Alice will tell each other what their A and B sequences are. That is, Alice will tell Bob her A sequence, Bob will tell Alice the B sequence. And what they will do is they will discard the bits, the X bits and the Y bits, whenever A and B are not equal. Okay, sorry about that interruption. But as I was saying, that what will happen after the bits have been sent, Alice will reveal to Bob over the classical channel her A sequence, and Bob will reveal to Alice his B sequence. And Alice will delete any element of the X sequence, and likewise Bob will delete any element of his Y sequence that corresponds to an occasion when A and B were different. They will only keep those values when A and B were the same. So for instance, Alice will discard this, Alice and Bob will both discard the first bits because A and B were not equal in that occasion, and so therefore it's unpredictable what Bob will have measured. Likewise for the third, and likewise for the fourth bit. In all these cases, A and B were different from each other. But in the second case, since A and B were the same, Alice and Bob both know what signal Bob received. Likewise in the fifth and sixth bits. But in the seventh bit, again, A and B were different, and therefore this would be discarded. And what will happen then is that after that's done, Alice and Bob will create an X prime and a Y prime sequence, and those will consist of what's left over after all the deletions. And in this case, it happened to be 1, 1, 1. So 1, 1, 1. And here for Bob, the Y prime sequence will be, he knows that this horizontal cat means this is a ket from the standard basis, and so this corresponds to a 1. Again, this is the second thing that Bob has left over, and again, it's from the standard basis, so it corresponds to a 1. And this is from the Hadamard basis, and for the 135 degree ket in the Hadamard basis, that corresponds to a 1. And so you see that the X prime and Y prime sequences of what's left over after deleting all the bits for which A and B are different, these two sequences will be exactly the same. Now, this certainly illustrates how Alice and Bob could come up with a sequence of zeros and ones, but the key now is to ask the question of, well, why is this private? How do we know that Eve doesn't know this sequence as well? So that's what we come to next. The key to explaining this is to remember that Bob and Alice, and likewise Eve, they don't know when their bases were the same and when their bases were different until after the corresponding bit has been sent. So in other words, when Alice, on this first bit, she sees A is equal to 1, therefore she chooses the Hadamard basis, and she will encode it. Since she wants to encode a 0, she will use the 45-degree ket. She will send that to Bob, and then he will choose a basis. Since B is equal to 0, he'll choose the standard basis, and then he will receive. But he will not reveal to Alice until afterwards, after he's already received that photon. He will not reveal to Alice until afterwards which basis he used. And that's the same for every single photon that is sent. Bob will not reveal that information to Alice until after the photon has been sent. Therefore, let's consider what Eve's situation would be if she were trying to intercept this information. Now, I'm not going to even worry about Eve intercepting one of the bits for which A and B are different, because Alice and Bob are not going to keep that information anyway. Any of these cases where A and B are different, that's going to be discarded and will not be part of the final sequence. So I'm not going to even worry about that. But let's suppose that here, in the sending of this second bit, that Eve, as we see up here, that Eve tried to intercept the photon that Alice sent to Bob. And let's see what would happen there. Okay, so since A is equal to 0, Alice will be using the standard basis. And since she wants to encode A1, she will be sending the horizontal ket. Now, if Eve, let's suppose that Eve knows what two bases Alice is using. Now, Eve does not know Alice's A sequence, so she would never know when Alice is going to use the standard basis and when she's going to use the Hadamard basis. Eve would have to guess. Half the time she would be correct on average, and half the time she would be wrong. So let's think about this. Okay, again, since A is equal to 0 for the second bit, Alice will use the standard basis, and since she wants to encode a 1, she would have the horizontal ket. Now, if Eve is lucky enough to guess that Alice would be using the standard basis, then since the standard basis was used to encode, to generate this photon, then Eve would receive this correctly. So on those occasions when Eve does choose the correct basis that Alice is using, the same basis that Alice is using, on those occasions she will get exactly the signal that Alice sent. And then she can likewise use that same basis to send the information to Bob, and she will not have disturbed it at all, and therefore Bob will receive that same signal. So no problem. Eve will not be detected. But what about on those occasions when Eve chooses the different basis from Alice, from what Alice used? Now again, remember, Eve does not know Alice's A sequence. So she has to guess at random what basis Alice is using to generate the photons. So let's suppose now that on this second bit, instead of guessing correctly that Alice would use the standard basis, let's assume that Eve chose to use the Hadamard basis. Well, in this case, if Eve used the Hadamard basis, there is a 1/2 chance that she would get the 45-degree ket, and a 1/2 chance that she would get the 135-degree ket. So there's a 1/2 chance that she would think that Alice is sending a 0, and a 1/2 chance that she would think that Alice is sending a 1. So therefore, Alice, has uncertain information there. Furthermore, think of what would happen if Alice read this 45-degree cat, which she would do on half of the occasions when she makes the wrong guess. Then she would send that 45-degree cat to Bob. Now, Bob, remember, is using the standard basis. Now, he might indeed, when this 45-degree cat comes in, he might indeed, since he's using the standard basis, he might indeed receive it as a horizontal cat. There's a 50% chance of that, but 50% of the time he would receive it as a vertical cat. And the same thing is true if if Eve had received a 135-degree cat. Again, then she would send this on, and Bob again would have a 50% chance of getting vertical, 50% chance of getting horizontal. So what we conclude is that whenever Eve uses the wrong basis, and that's going to happen on 50% of the photons that she tries to intercept, then Bob will only have a 50% chance of arriving at the correct bit that Alice is trying to encode, regardless of which value Eve uses to send to Bob. So again, there's a 50% chance that Eve is wrong, and then on 50% of those occasions when Eve is wrong, Bob will end up concluding the wrong bit. Even though he and Alice might be using even though he and Alice are using the same basis, 25% of the time, he will end up getting a different bit from what Alice intended because of Eve's intervention. And so this tells us how Alice and Bob can detect whether or not anybody has been trying to intercept their signal. And it goes as follows. After Alice and Bob arrive at their X prime and Y prime sequences, then they compare the first few bits. Now remember, these should all agree, because these are the sequences that were obtained when Bob and Alice used the same basis. But if they detect differences in these, and if Eve is trying to intercept, then 25% of the time they will notice differences. Then they know that there is some unknown person trying to intercept the signals that they're passing, and therefore they know that they cannot trust the key that they have established, and therefore it fails. They'll have to wait for some other occasion and hope that no interceptor is listening at that time. And so that is an example of how the BB84 protocol would work. And I want to now give you some problems on it, but before I do, I want to look at one more example. So the example that I would like you to consider, and I think that if you understand this example, it will show that you thoroughly understand this idea of the BB84 quantum key distribution protocol, is the following. Let's say that Alice's X sequence, her initial X sequence, not X prime now, but X, is 1, 1, 0, 0, 1. And that her A sequence is 1, 0, 1, 0, 1. And let's say that Bob's B sequence is 1, 1, 1, 0, 1. And furthermore, Eve is not present, so there's no interception. Now, if that is the case, which one of these four, or excuse me, I'll say that it could be more than one. which of these sequences represent possible Y sequences? Now remember, the Y sequence is what Bob measures. And which ones of these represent possibilities? And I'll help you sort through this. Notice that for each one of the choices, the first bit is corresponds to the 135-degree ket. And the third one for each one is the 45-degree ket. The fourth one is the vertical ket, and the fifth one is the 135-degree ket. So these four sequences are exactly the same in the first, third, fourth, and fifth bits. They differ only in the second bit. For A, we have the vertical ket. For B, the 45-degree ket. For C, the horizontal ket. And for D, the 135-degree ket. So which of these sequences would represent possible Y sequences? Which ones of them would not? So I want you to answer that first. And then for those that do represent a possible Y sequence, tell what the corresponding Y prime sequence would be. So I urge you to stop the video now and take a careful look at this, and then after you think you have the answer to both of those questions, then come back. So please stop now. Okay, I hope you had luck with that, and I hope also that you very quickly realized why these four sequences differed only in the second bit, and that is because that was the only occasion in which A and B differed. A and B are both equal to 1 for the first bit, and for the third bit, and for the fifth bit, A and B are both equal to 0 for the fourth bit. The only bit for which they differ is 0 and 1. So let's go through the other bits first and make sure we understand this. Since all of these sequences are the same in the first, third, fourth, and fifth bits, let's just go ahead and look at option A here and see if we can understand the first, third, fourth, and fifth bits. So for the first bit, Alice has A equal to 1, so she will use the Hadamard basis. And remember, for the Hadamard basis, when she uses it to encode a 1, she'll have the 135-degree ket. And so she'll send 135. Bob is using exactly the same basis to receive, so he gets 135. So this first bit is correct. We'll skip over the second one because A and B are different there. For the third bit, again, A and B are both 1, so both Alice and Bob will use the Hadamard basis. Alice wants to encode a 0, so she'll use the 45-degree ket, and that is exactly what Bob will receive. So the third bit here is explained in that way. For the fourth bit, A and B are both 0, so both will use the standard basis. And when Alice encodes 0 in the standard basis, remember she will encode it as the up or vertical ket, and therefore Bob will receive it as the vertical ket, so this is correct. And then for the final one, Bob and Alice are both back to using now the Hadamard basis, and Alice wants to send a 1, so that's 135-degree ket, and that's the way that Bob will receive it. So it looks like the first, third, fourth, and fifth bits in all of these sequences are correct. And now we need to look at what might happen in the second bit. Now I hope you understand right away that since A and B are different, we can't say for sure, that is, since Bob and Alice are using different bases here, we can't say for sure what Bob will measure. but we can say for sure what the possibilities are. And first of all, let's just realize that since Bob is measuring, see, B is equal to 1. And therefore, that means that Bob is measuring in the Hadamard basis. And if he's measuring in the Hadamard basis, then he has to be measuring either the 45-degree ket or the 135-degree ket. And therefore, when we look at A, where Bob is supposedly measuring the vertical ket for the second bit, that is impossible. And likewise, he could not be measuring the horizontal ket either, because that is not one of the vectors in the Hadamard basis. Now, when we come over here to options B and D, the 45-degree ket that we see in option B and the 135-degree ket that we see in option D, both of those are vectors in the Hadamard basis. So these are legitimate possibilities that Bob could measure. And in fact, there would be a 50% chance that he would measure this one and a 50% chance of this one. So the correct answer to the first question is that B and D are the correct answers. They are the two sequences that Bob might indeed measure. And now, what would be the corresponding Y prime sequence? Well, remember that the Y prime sequence comes from the Y sequence and also from taking into account when A and B are different. So since A and B are the same for the first, third, fourth, and fifth bits, we will retain in Y, in this Y sequence, we will retain the first, third, fourth, and fifth elements. But the second one we will discard because we're not sure if it is correct or not. So we want to retain this, this, and this, and then we want to translate those into the correct bits. And we know that, for instance, the 135-degree ket would be encoded as 1. We discard the second bit. The 45-degree ket is 0. The vertical ket corresponds to 0, and the 135-degree ket 1. And so this is what is left over. This would be the Y prime sequence, and this is also the X prime sequence. And you can see that coming up here to the X sequence. And after we delete that second term, we're left with 1, 0, 0, 1. As we said here, 1, 0, 0, 1. So this is the X prime sequence and also the Y prime sequence in this case where there is no interception. Now, we want to look at this same problem, but let's assume that there is the possibility of interception. So let me break for just a moment, and then we will return to this. So in this final example before the problems, we will assume that the X, A, and B sequences are exactly the same as they were in the previous example. The only, in this example up here, the only difference is that now, in this case, we will assume that Eve is intercepting. And furthermore, since Eve is intercepting, she has to have some measurement basis, and we will assume, as we did in our previous discussion, that she knows that the two bases that Alice is using are the standard basis and the Hadamard basis, but she doesn't know when Alice uses which. So therefore she'll have to choose which basis to use randomly, And so I have also made an E sequence which will determine which basis Alice will use. And when it's 1, she will use the Hadamard basis, and then when it's 0, she will use the standard basis. And notice that with the numbers that I've given, Eve has been fairly lucky, because for the first bit, Eve has chosen exactly notice that A and E are both equal to 1. And likewise, for the 4th bit, A and E are both equal to 0. And for the 5th bit, A and E are both equal to 1. So the 1st and the 4th and the 5th bits, so 3 out of the 5 bits, Eve has chosen in a fortunate manner and will be using the same basis as Alice. But in the second bit, A is equal to 0 and E is equal to 1. So in that case, Eve and Alice will use different bases. And also in the third bit, Alice, A is equal to 1, E is equal to 0. So in the third bit, they will also use different bases. So now, I want you to, first of all, just as we did before, I want you to look at these 5 sequences and tell which of those, and it may be more than one, which of those represent possible Y sequences for Bob. And let me point out also that all of these sequences agree on the first element, that's the 135-degree ket. All of them agree on the 4th, being the vertical ket. All of them agree on the 5th, being the 135-degree ket. The only places in which they differ are in the 2nd and 3rd elements. Here we have 45-degree, 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 135-degree, 135-degree, 135 degrees, 135 degrees, and 45 degrees. So you need to look at these possibilities and decide which ones are possible sequences measured by Bob. Do that first, and then we'll ask for each one of those what the corresponding Y prime sequence is. So please stop the video now, give this some careful thought, and then we'll come back and look at this together. Okay, I hope that after thinking about this carefully, you have decided that all 4 of these sequences are possible sequences measured by Bob. And let's understand why that's the case. Well, first of all, since Eve has chosen to use the same basis as Alice, or not, well, yes, chosen, but it is according to this random string E. But since Eve has been fortunate enough that her value for E matches the value of A for the first bit, the 4th bit, and the 5th bit, and since Bob's value for B also matches the value for A for the first bit and the 4th bit and the 5th bit, then for the first bit and the 4th bit and the 5th bit, both Bob and Eve will receive exactly what was sent by Alice. And so that will be the 135-degree ket for the first bit, the vertical ket for the 4th bit, and the 135-degree ket for the 5th bit. And so that's why in all 4 of these sequences, the first bit, the 4th bit, and the 5th bit have been chosen to be the same, and these are all the correct answers. But now let's try to understand why when we look at the 2nd and 3rd bits, we're getting all 4 possible combinations here. Well, first of all, Bob is measuring the 2nd and the 3rd bits. For both of those, B is equal to 1. So he's using the Hadamard basis for both of those measurements. And so for sure, he will be getting either the 45 degree or 135 degree cats. He will not be getting vertical or horizontal cats. But that's fine, because in each one of these cases, these vectors that are being proposed as being received by Bob, they are vectors in the Hadamard basis. So we can't eliminate any of these possibilities on that basis. So now let's proceed. Well, let's look at the second bit in a little more detail. Alice has A equal to 0, and therefore she's going to use the standard basis. She wants to encode a 1, so she'll send a horizontal ket. But Eve is going to intercept that. And Eve is using a different basis from Alice. Since E is equal to 1, Eve will be using the Hadamard basis to intercept that horizontal ket. And since she's using the, you might say, inappropriate basis, she will be half the time getting 45 degree ket and half the time getting 135 degree ket. Now, Bob is also using the Hadamard basis, so Bob will be receiving whatever Eve sends. But what Eve sends, as we just said, it will be either the 45 degree ket or the 135 degree ket. So we don't know for the second bit, it'll be either 45 degree ket or the 135 degree ket, but we don't know which. So we cannot eliminate A or C or B or D. We can't eliminate any of those on the basis of their value in the second bit, because all four, well, both of these are possible. The 135 degree ket, which we have in A and B, 45 degree ket, which we have in A and B, or the 135 degree ket, which we have in C and D. So now let's look at the third bit. What's going on there? Well, here you would ordinarily think, since Alice and Bob are using the same basis, you would think that Bob would get exactly what Alice intended. However, Eve is intervening, and she has the wrong basis to intervene, and so that's why there's uncertainty here. Let's look in a little more detail. Okay, Alice has A equal to 1, so she will use the Hadamard basis, and since she wants to encode a 0, she will encode that as the 45 degree ket. That 45 degree ket will be intercepted by Eve, but Eve is using the standard basis. So when she intercepts a 45 degree ket with a standard basis, half the time she will read that as the horizontal ket, half the time as the vertical ket. And then she will send whichever one of those to Bob, but Bob is using a different basis from Eve. And so for both of these possible kets that Eve will send, sometimes Eve would send the vertical ket, sometimes she would send the horizontal ket, and for both of those, since Bob is using a different basis, he would have uncertainty as well. Half the time he would get the 45 degree ket, and half the time the 135 degree ket. So it's possible he could get this 135 degree ket there, or there. It's also possible he could get the 45 degree ket there and there. So we cannot eliminate any one of these possibilities. All four of these sequences represent possible Y sequences for Bob. Now, which ones represent possible, what will be the corresponding Y prime sequence that Bob would have for each one of those? Well, remember, the Y prime sequence is determined from the Y sequence after Bob and Alice have compared notes and have determined for which bits their values of A and B agree. Now, as before, as in the previous example, A and B agree on the first, third, fourth, and fifth bits. They disagree only on the second bit. So the second bit is the only one that Bob and Alice would discard. So when we take out that second bit from each one of these sequences, we're left with what's shown up here. And so now if we write down the corresponding Y prime sequence for A, that would be 1. Here's 1, 0, 0, here, and 1. For B, the Y prime sequence would be 1, 1, 0, and 1. For C, it would be 1, 1, 0, and finally 1. And then for D, it would be 1, 0, 0, and 1. So we have two of these would yield the Y prime sequence 1001. A and D would yield 1001, and B and C would yield 1101. Those would be the two possible Y prime sequences. Now for Alice, everything is exactly as it was before. She doesn't know anything about Eve's presence, so the X prime sequence would still be 1001. And so now you can see how Eve's presence might be detected even on as short a sequence as the ones we're looking at here, because yes, Bob might end up with 1001, which was exactly what Alice had, but he also might end up with 1101, and if he did, then if let's say that after Bob and Alice have determined their prime sequences, if they decided to share the first two of those, then they would notice that that second bit was different. And that would, in other words, if Bob chose this one, if Bob received this one, then the 1 would be different from 0. That would alert them that there was a problem. Now notice though that there is a possibility that Bob would have 1001, and so if that were the case, and he and Alice had such short sequences, then the intersection would not be detected. So this is the way that the BB84 quantum key distribution protocol proceeds, and how it ensures privacy as well. And so now let's look at some problems. So now finally let's look at the problems for lecture 6, and they are very similar to the examples that we just considered. For the first two problems, Alice's X sequence is given here, her A sequence is given there, Bob's B sequence is given here, and there is no interception, and you should circle all of the possible Y sequences there. All of those, there may be more than one, each one that represents a possible Y sequence you should circle. And likewise here for 6.2, which represent a possible Y prime sequence. Sorry about this. This should not be there. So that's those are problems 6.1 and 6.2, and then for problems 6.3 and 6.4, exactly the same as in 6.1 and 6.2, except that now Eve is intercepting, and she chooses her basis according to the variable E, for which the sequence is 1, 1, 1, 0, 1. And so now again, identify all of these sequences that represent possible Y sequences should be circled, and similarly you should circle all of these that represent possible Y prime sequences. So I really hope you have luck with this and have understood this, what seems to me to be a very interesting concept. And that concludes Lecture 6. Good luck.